Yay!
In finding the magnetic field from currents, one of the most useful examples that we'll do is going to be finding the magnetic field from a loop of current, because it turns out that's really, really common. So let's do that real quick. Suppose I have a loop in the xy plane carrying current I. And then what I want to do is find out right up here on the z-axis. So this is sort of like the electric field example for a ring, right? Up on the z-axis, I want to know what the magnetic field is due to this current loop. So we do the same kind of thing. We're going to divide this thing up into lots of little dLs, right? And then we're going to integrate the magnetic field from each little bit. So the total magnetic field is just going to be the integral. We're going around in a circle, right? So in some sense, we're going to want to do like 0 to 2 pi. And the magnetic field is mu naught. The Biot-Savart thing is mu naught over 4 pi. Let's see, I'm going to have my I over, I'm going to write it this way, r cubed, and then I'm going to have, normally it'd be L cross r, but this is dl, because we're doing lots of little ones, across the r vector. So let's do it that way. Look, all of this stuff out front, all that stuff, it looks like this can be pretty easy, because all that is just constants, right? Mu naught, I is the same everywhere, 4 pi. R cubed, r is this distance from that little bit up to the point we're interested in. And that doesn't change as we go around the loop, right? So all that stuff is just going to come out front. It's this thing that we're going to have to be a little bit more careful with, because we're integrating that cross product as we go around the circle. I mean, normally that would involve, you know, some sines and cosines and all that, but let's be kind of like what we did before with the electric field. Let's be a little bit clever. Let's see if we can use symmetry to maybe make that a lot easier, so we don't actually have to integrate stuff. Okay, first thing is we're going to need the cross product, A cross B. And remember, how I like to do that is I just draw a circle. I'll do it again here real quick. And this circle, I just write x and y and z. It's just a cycle going from x to y to z and then back to x. So that tells me the order that I write down these first bits of the components. So A cross B, I start, if I want the x component, I just start there and start going around the circle. So the x component is a y b z minus a z b y. The y component, I just go around the circle, is a z bx minus a x bz. And then the z component is just a x by minus a y bx. Okay, neat. So what I want is dl cross r. Okay, where I have that thing drawn, that dl right there, that thing is going to be tangent to the circle headed off, oops, tangent to the circle headed off that direction, right? That's going to be the direction of that dl if I would draw the circle right. And then I want to cross it with the r vector. Okay, so let's just compute it just for kicks. Let's see. In fact, what I'm going to do is let's call that position A, let's call that B, C, and D. Okay, so at position A, let's actually compute this cross product and see what we get. So we're not integrating, we're just going to get the cross product. So what do I get? dl cross r, let's see. dl, it's just pointing in the y direction, and it's got magnitude dl, so it looks like it's going to be 0, dl, and 0. And then I'm crossing it with, well, what is r vector from that point to the point I'm interested in? What do? I have to go back, big R, the radius of the thing. I have to go back in the x direction, minus r. I don't do anything in the y, and then I go up z in the z direction. Right? That's the vector to get to where I want to go. So when I do this, let's see what I get. I only, let's see, DL is in the Y, right? So I only involve Y components. So it's just going to be in the X, I'm going to have AYBZ. So that's ZDL. AZBY, nothing. AZBX, nope. AXBZ, nope. AXBY, nope. And then, so there's no Y component. And in the Z component, AYBX, it's a minus, minus. So it's a plus RDL. There we go. So that's what I get for that DL cross R, right? Okay. So just to illustrate what's going to happen, let's look and see. Let's take the mirror image of that thing. So let's look at what happens here at C, right? Because that's my DL over there at C. That's the direction of it. So just for kicks, let's look at what I get at C, because now DL just flips sign, right? It's going the opposite direction. That's all that's happening. And my R vector, what's happening in the R vector? What's happening is that now I have to go plus R and 0 and Z. And so when you do this, what's happened is that the DL switches sign and the R switches sign, right? Well, that doesn't change the Z component. If I switch both of those signs, I still get that. But up here, I get minus ZDL. Okay, so as I'm doing the integral, what I'm doing is adding all of these things together, right? Well, this part and the part, its mirror image on the other side, A and C, if I add those together, look what happens. The X component goes away, right? All I'm left with is that common factor, that Z component. It turns out that you're going to get the same thing. I will invite the interested viewer to do the same thing with B and D. What you're going to get is you're going to get Y components, and those Y components are going to vanish, but the Z components are going to be the same. So as you go around that circle, everyone is going to cancel with the symmetric neighbor across the circle, but except for the Z component. Z components always add. So we're always going to get this little factor at the end. In fact, that's what we get when we add all of these vectors together. That's the result. So what we can do then is we can say that the magnetic field is, let's bring all this stuff out. Mu naught I, R from that vector comes out, and I have 4 pi R cubed. Let's see, R is, what is that? That's the hypotenuse of Z and R, right? So it's just going to be R squared plus Z squared to the 3/2. That's that R cubed. And then I'm going to have 0 to 2 pi, and all I got left in here is just DL. That's it. So this integral really became something pretty simple. What is it? Well, that's just DL. That's just integrating the length all the way around a circle. That's just the circumference of the circle, right? So that's just going to give me 2 pi. So finally, we actually didn't have to do much work after all, right? The nice thing is that by invoking symmetry arguments, we don't actually have to integrate stuff. So this is going to be mu naught I R times 2 pi R divided by 4 pi R squared plus Z squared to the 3/2. Okay, well, I guess I can combine stuff together, cancel stuff out. So this is going to be mu naught I R squared. The 2 pi and the 4 pi are going to cancel to make a 2 R squared plus Z squared to the 3/2. Oh, I keep saying this is a vector, right? I should, I suppose, write that this is in the Z hat direction. Okay, so there it is. There's the magnetic field due to a loop of current. There's a couple interesting things we can do with this. One is, what happens when Z is 0? I mean, this should work for any Z you want. So when Z is 0, in other words, at the center of the circle, what do we have? When Z is 0, let's see, that's just going to be R squared to the 3/2. So that's r cubed. Well, I got an r squared in the numerator, so this just becomes, the magnitude is just going to be mu naught I over 2r. Look at that. That becomes really easy. So at the center of a loop of current, there's the magnetic field magnitude. And the other interesting thing we can do is, let's look and see what happens if Z is a whole bunch bigger than R. So when we're far away from the loop, how does the magnetic field behave? So in that case, B will be approximately, let's see. So if we do that, the Z term is going to dominate. So that's going to be mu naught I r squared over 2Z. Let's see, mu naught r squared over, this is going to be 2 Z cubed. So that's kind of cool. So the magnetic field is going to die down like an electric dipole field, which is kind of not a coincidence. But anyway, so the magnetic field is going to go down by 1 over Z, 1 over the distance cubed. So if I go twice as far away, the field is going to die down by a factor of 8. 3 times further away, it goes down by a factor of 27. Cool. And there's also something else that pops up. I'm going to write this in a slightly different form because this is probably what you're going to see. Look at that IR squared in the numerator. That's almost, what if I multiply the top and the bottom for no reason by pi? So on the top, that would give me I pi r squared, right? Pi r squared, that's the area of the loop. So let's write it like this. What if I said it's mu naught I times A, the area of the loop, and then on the bottom, I'm going to have 2 pi Z cubed. This thing, I times A, that's a new thing. Called the magnetic moment. The magnetic moment of the loop is just, it's basically everything you want to know about the loop. How much current does it carry and how big is it? Those are the things you want to know to figure out the magnetic field of the loop. So the magnetic moment, it's just I times A. So if I want to write it, I could write it like this in terms of the magnetic moment. And again, the only reason I'm doing it is because the magnetic moment is just something you're going to see more and more as you go along, because it completely describes the magnetic field you get from the loop. It's just based on the geometry, just how much current it's carrying, just the physical properties of the loop, how much current it carries, and then what its area is. Okay, so what's coming up next is what happens if we stack a whole bunch of these loops together? What if we have n loops? Well, if they're all, like if the loops are just right on top of each other and don't take up much space, then you just multiply the magnetic field times n. So you can make a much stronger field just by having lots of loops all in one place. But if we stack them along a cylinder, then we get something else called a solenoid. And then we're going to have to do something a little different to figure out the magnetic field. So that's what's coming up.